SwayamPrabha. Digital India. Educated India.
Hello students, today's lecture we will be studying classification of nanomaterials. So, nanomaterials will be studying the classification, and nanomaterials can be classified into 0, 1, 2 and 3 dimensional nanomaterials, as I have already told you before, but we will be discussing that in detail now, and we will also be studying natural versus engineered nanomaterials. So, we will be studying what natural nanomaterials are and engineered nanomaterials are and the difference between them. So, why do we need to classify nanomaterials? Why is it important to have a proper classification for nanomaterials? So, there is a wide variety of nanoscale structures and compositions all around. So, as I have already told you, you have been using different synthesizing techniques to obtain different shapes and sizes and whatnot. So, nanomaterials have a wide diversity of structures and composition and properties as well. So, you need to classify them properly to create a better understanding of the structure property relationships of these nanomaterials. So, this guides the selection for specific applications. So, this classification will help you to determine what kind of nanoparticle has to be used for any specific application. So, it is also essential for nanobiotechnology design and regulation. So, let us begin with the dimensional classification of nanomaterials. Based on the number of dimensions your material is confined to the nanoscale, you can divide them into various classes like 0 dimensional nanomaterial, where all dimensions are less than 10 to 100 nanometer, and maximum, basically the maximum value is 100 nanometer. So, 1 dimensional nanomaterial where one dimension is greater than 100 nanometer. Then 2 and 3 dimensional nanostructures where 2 dimension is greater than 100 nanometer, and 3 in 3 there are 3 dimensions greater than 100 nanometer. So, we will be studying these in detail. So, that is your scale x, y, z axis, and as I have already told you about quantum confinement, that when you prepare a nanoparticle or nanomaterial from a bulk structure, the free electrons are now confined to a very small space. So, they have they have that energy to move to the higher energy levels, but they cannot, because now they are confined with some impenetrable walls of infinite energy. So, now they are confined into this, it is like a particle in a box model of quantum physics, and it is confined to this small space. So, now they have 3 axes to move, but they cannot move when we are considering 0 dimensional nanoparticles. So, this is a bulk material and you create a 0 dimensional nanoparticle, it is over here. It cannot move in this direction or this direction, it is confined to 0 dimension, it is over here. So, that is our 0 dimensional nanomaterials, which include carbon dots and structures like that which have 0 dimension. Electrons are confined in all 3 directions. Electrons cannot move over here, they are confined to one direction. Now, remember the definition of nanomaterials, where at least one dimension has to be in the nanoscale. So, at least one dimension has to be of the size 10 to 100 nanometer, but there can be other, the length can be, the width can be, there can be other things that can be of the so, that is the 0 dimensional nanomaterial. Then there can be a 1 dimensional nanomaterial where the length, the electron is not confined along the length. So, in 1 dimension electron can move, like it can move along one axis, but it is confined in 2 dimensions. It is confined on z and y axis, but it is not confined along one axis, that is x axis. So, it is like a wire, you consider a thin wire. So, if you see electron is confined in 2 directions, if you consider this to the nanoscale level, so it is confined in 2 directions, but it is not confined along the length, that is along this line. So, that is 1 dimension. Then you consider 2 dimension, where you consider this plate, rectangular plate like a board. Put it over here and you will realize that in two directions the electron is not confined, it is confined in just one direction. Iska depth jo hai, that is almost, that is zero dimension. What we are considering, if we are considering nanosheets, then we see that there is no depth, there is zero depth, that is zero dimension. Like it along one axis it is of the zero dimension, and in two directions it has dimensions. Electron is not confined on this axis. On this axis it is confined along the width. So it's like this. That's a plate. Your electron is not confined along this, but it is confined depth wise. So that is two-dimensional nanomaterial. So these include nanosheets, and then it can be three-dimensional. So nano materials, basically the three dimension, when they include, they are not confined in any of the three dimension. They can be formed from 0 dimension or 1 dimension or 2-dimensional materials. 3-dimensional materials can be made. Now electrons are not confined in any direction. They are free to move in all three axes, which is like this. So that is 0-dimensional nanomaterial, which is confined in all three directions. The electrons are limited. They cannot move, they are confined in all three directions. Then comes nanowires, 1-dimensional. There electron is, the movement of the electron is free along the line. Across one axis, the movement of the electron is free, but on two axes, the movement of the electron is confined. Along two axes, the movement of the electron is confined, but along one axis, it can move freely. So that is 1-dimensional nanomaterial, that is nanowires and all. Then comes nanosheets, that are 2-dimensional materials. Here your electron, the movement of your electron is confined along this direction, but not across the width. So in one direction your electron is confined in 2-dimensional nanomaterials. Then in 3-dimensional nanomaterials, your electron is not confined in all three directions. It is free to move in all three directions. So that's a chart. So dimension type can be 0 dimension, 1 dimension or 2 dimension. 0D materials, basically the nanoscale dimensions are length, width and height. So the length is also 0 dimensional, width is also 0 dimensional and height is also 0 dimensional. Then the structure description, it is confined in all directions. So it is confined along the length, along the width, along the height, it is confined in all directions. So it is, as the name suggests, it is 0 dimensional. So it has no dimension in any of the direction. So common examples are quantum dots, metal nanoparticles, these are all 0 dimensional nanomaterials. Then key properties, basically they have like I have already told you in quantum confinement, they electrons that when they get confined to a very small space, to nanoscale, when the material's size becomes comparable to the de Broglie wavelength of the electron, so the electron has the same Fermi energy that the bulk material was having. So it creates a discrete energy levels. So unlike where the bulk material has continuous energy bands, the electron now has discrete energy levels or distinct bands, and the distance between the conduction band and valence band increases. So the electron will need high energy to jump from the conduction band to the valence band. So a high energy is required for the electron to jump from conduction to a valence band. It jumps from there and then comes back to the ground state, and that is how fluoroforms are formed, because a high energy is released when your electron jumps from a lower energy level. Then strong optical absorption. This happens because, so your electron now has discrete energy levels. So earlier when you were considering bulk material, you had a ramp like energy level that was continuous, and also the distance, these are the energy levels of the electrons in a bulk material. So now that is the energy gap. Okay. That is the energy gap. Now this is nanoscale material, and now you have discrete energy levels, and that is your valence band, that is your conduction band, and as photon strikes, your electron gets excited over here and it gets excited, and now as the distance between these bands is higher, now it has to literally jump from here to here, and now here a hole is created, that is known as a hole, and this electron and hole is known as exciton. Okay. So, this electron and this hole pair together they make exciton. So, your electron has jumped over here, it took the high energy, jumped over here, then when it jumps down from over here to here, it comes down to mostly lower energy levels and it releases light. That is light that causes the photoluminescence property of the nanomaterials. So, that is how it works. So, these are the discrete energy levels that are the key properties of our nanomaterials. So, now dimension type is 0D, nanoscale dimensions basically restricted along length, width and height. Description is that it is confined in all directions. Common types, quantum dots, metal nanoparticles, and key property is that they have discrete energy levels and strong optical absorption. Then comes dimension type 1D, one dimension. So, one dimension nanoscale dimension is basically diameter only. There is only one nanoscale dimension, that is that is along the diameter. So, it has a length, but it is confined along the diameter. So, in two axes it is confined, but along the length it is not. So, structure description is that long wire-like structures can be formed. So, when you consider a nanoscale, long wire-like structures are formed in one dimension. Common examples are nanotubes, nanowires and nanorods. Key properties are that high aspect ratio and directional conductivity. So, you want a nanowire which has a directional conductivity, a conductivity in one direction, in the direction you want it to be. So, you consider one dimensional nanomaterials. So, according to the use, you create nanomaterials and you classify them. Now, there is 2 dimensional or 2D dimension type. So, the nanoscale dimension is thickness only. So, it is your nanoscale dimension is just thickness only. In 2 directions, your electron is not confined, it is only confined along the thickness only. So, in 2 dimensions, your electron is not confined. और इसमें in one direction your electron was not confined, इसमें in any direction, in all directions your electron was confined. Your electron was confined in all directions. That was 0 dimension. It could not move in any direction. One dimension is where it could move only in one direction. So, confinement was in 2 directions. Now, your confinement is in one direction. In 2-dimensional materials, your confinement is in 2 directions, but your electron can move in, your confinement is in one direction, but your electron can move in 2 directions, along the length, along the width, but in thickness only it is confined. And then structure description is that sheet-like or layered substance, sheet-like or layered nanomaterials are formed with 2-dimensional property. Then common examples is graphene, magazines or thin films. Key properties is high surface area, excellent mechanical strength. You want something with a high surface area and excellent mechanical strength, you consider 2-dimensional nanomaterials. So, you first need to know what properties you want to manufacture in a material, what properties you need in a nanomaterial, then accordingly you classify the nanomaterial, then you create that nanomaterial. This is the reason why we classify nanomaterials. That's again the same explanation to give you a proper insight into this. So, these are 3D materials where the movement of electron is in all 3 directions, it is not confined in any direction. You can see it clearly now, x, y, z axis. Then there are 2-dimensional materials, x, y, z axis, and this direction electron is confined, and in 2 directions it is not. Then there are 1-dimensional materials, electron motion is confined in this direction, in this direction. In this direction it is not, it can move along this direction. Then there are 0-dimensional materials where the motion of electron is confined in all directions. Now, in this material, your electron cannot move in any direction. It is confined over here. So, it cannot move in any 3 directions. It is confined in all 3 directions. These are the examples: quantum dots, might look like this. That's an AI generated image to give you just an idea of what it looks like. So these are the 0-dimensional nanoparticles, quantum dots, 1-dimensional nanowires or nanotubes, or 2-dimensional nanosheets or graphene sheets. You can see these might be the carbon-carbon bonds and a graphene sheet. So 0-dimensionality, 0D, 1D or 2D. Nanoparticles, quantum dots are 0-dimensional, nanowires, nanotubes are 1-dimensional, and 2-dimensional graphene or these sheets are basically 2-dimensional. That's a nanosphere in 0 dimension, that's a nanotube. In 1 dimension, you can see the structure, carbon ring structure, you can see. So that's a nanotube which is still in 1 dimension, and it can be in 2 dimension like a sheet of paper, which is in 2 dimension. So these are the carbon-carbon bonds, that is a graphene-like structure which is spread along 2 dimension and confined in 1 dimension, that is a nanosheet. Then there can be interconnected structures, these form the 3D dimension. The 3-dimensional nanomaterials, if it is difficult to understand, it's like interconnected structures. So your 0-dimensional, these materials can be interconnected and they form a 3D structure. So that's a picture, 0-dimensional nanoparticle, that is 1-dimensional nanoparticle. These are the nanofiber, and it can be 2-dimensional sheet and 3D nanomaterials look like this. An entire crystal, it's like a tight packing of, this is like a tight packing of a 2D nanomaterial. So this forms a whole 3D structure where your where all three, in all 3 dimensions, your electron is free to move. That's again a nanosphere, that's a nanofiber, that's a nanosheet, and that's a mesoporous structure. That's in 0 dimension, that's in 1 dimension, that's in 2 dimension, that's in 3 dimension. Or a core shell that I'll be teaching you in my later lectures, catalytic nanomaterials, that's a core shell. So that's in 0 dimension, that's in 1 dimension, the nanoporous fiber, it's in 1 dimension, that's in 2 dimension, nanoporous sheets. Then these are in 3 dimension metal organic frameworks. These are being widely used, metal organic frameworks. So it's important to know the dimensionality of it and the classification, because we've been classifying, there's a wide variety of nanomaterials. These are actually being used in various applications. So it's important to know how we classify them and how they look like. So that's a yolk shell. That's 0 dimensional, that's a nanotube. It's like you folded a paper, it's like a nanotube. That's a 1 dimensional material. Then there are 2 dimensional, these are hexagonal plates, these are nanoplates, 2 dimensional. Then there is a nanostructure assembly of materials, these are 3 dimensional. So that's the basic classification. These are the 0 dimensional carbon forms. So your 0 dimensional nanomaterials, here the starting material is carbon. You are making carbon-carbon bonds and creating 0 dimensional carbon forms. These are the carbon quantum dots. These are the carbon quantum dots which are 0 dimensional. Then there can be carbon nano onion. It looks like this. Then there can be a nanodiamond, that's also a carbon compound. It can be a nanodiamond. Like I've already told you, the properties change drastically when you create a nanodiamond from a diamond. Its elasticity differs and its hardness differs. So that's a nanodiamond. Then these are carbonized polymer dots. And then these are fullerenes. Fullerenes are important. So you can see the structure of a fullerene, it's like this. So all these are 0 dimensional forms. Okay. That's a graphene quantum dot. That is how some 0 dimensional carbon forms look like. Then 1 dimensional nanomaterials, as I've already told you, 2 dimensions at nanoscale and 1 extended dimension. Examples are nanowires, nanotubes and nanorods. Then anisotropic, electrical and mechanical properties. So you use them specially when you for conductivity and all, and where you need a movement of electrons in one direction. Then it's important for nanoelectronics and biosensors. That's a picture, like that's a crude image, but it's like that is how a nanowire is supposed to look like. These are nanorods, these are nanotubes. Okay, silicon nanowires, it can be gold nanorods, or these are the examples basically. Silicon nanowires, gold nanorods and carbon nanotubes. These are the examples. So silicon nanowires, what are these? These are conductive nanowires that are used in nanoscale electronic devices and sensors. So silicon nanowires are already in use. These are the conductive nanowires used in nanoscale electronic devices and sensors. Then gold rods are nanoscale rods that are used in biomedical imaging, photothermal therapy and sensing. So, these are gold nanorods and they are used in nanoscale rods used in biomedical imaging, photothermal therapy and sensing. And these are carbon nanotubes. These are tubular carbon structures known for their strength, conductivity and versatility. These are the various example of basically one-dimensional nanomaterials. These can be nanowires, nanorods or nanotubes. That is an electron microscopy image. As you can see, like I told you about zero-dimensional nanoparticles, that is a electron microscopy image of these nanoparticles. So, this is how they actually look like in a microscope. So, it is hard to imagine, you cannot see nanoparticles, so you can only correlate. So, when you see it with a electron microscope, this is how they look like. That is what I told you about. This is a pictorial representation, zero-dimensional nanoparticles, this is how they look like, and that is a scale bar. So, you see the size and the structure of the nanomaterials can be calculated from this, and these are zero-dimensional nanoparticles. These are how nanorods look like under a microscope, under an electron microscope. This is how nanorods look like. Then these are also nanorods. This is how they look like. These are nanowires, and these are nanotubes, and these are also nanowires. So, this is how they look like under microscope. So, that is a graphene sheet, a two-dimensional nanomaterial. That is a multi-layered graphite formed from the graphene. So, you can see how 2D structure is being converted into 3D. So, this can be rolled up into single walled carbon nanotube. That is how nanotubes are formed. So, when you fold a graphene, you roll up a graphene and you will obtain a single walled carbon nanotube. But if you roll up a graphite sheet, you will obtain multi-walled carbon nanotubes. So, that is how single walled carbon nanotube is formed. That is how multi-walled carbon nanotubes are formed. So, this is formed from graphene, that is formed from graphite, and if this is multi-layered, it forms the graphite. So, you see how various structures can be formed from this two-dimensional graphene. So, two-dimensional nanomaterials, basically thickness is confined to a nanoscale. Examples are graphene, nanosheets and thin films. It has a high surface area and mechanical strength. Applications are in membranes, electronics and biomedicines. That is an example of two-dimensional nanomaterials. Of various shapes and sizes. These can be metal organic frameworks or magazine or covalent organic frameworks. These can be like this, and emerging nanostructured 2D materials for bioelectronics. They can be used as implantable devices, as disease sensors, as memory transistor, neural interfaces, sweat sensors and neuromorphic computing, tactile sensors or voice sensors. So, these emerging nanostructured 2D materials have been used for bioelectronics. They have already been used and they are still being made. Sweat sensors were recently talked about, where you use a sweat for sensing some any infection that has started. So, earlier you used blood, then you use saliva, and now even sweat can be used for sensing that. So, you use sweat sensors to sense the sweat for any viral infection or any infection that has occurred in the body. So, that is how. And then there are implantable devices. All these are already widely in use. Then three-dimensional nanomaterials. These are nanostructured bulk materials. Nanostructured bulk materials, examples are non-porous, nanoporous materials, nanocomposites, nanoscale features embedded in macroscopic form. These are basically 3D nanomaterials are basically nanoscale features that are embedded in microscopic forms. So, these are macroscopic, but nanoscale features are embedded into it. Enhanced mechanical and functional properties. These have highly enhanced mechanical and functional properties. Rather than a bulk material, rather than a macroscopic material, we are talking about some nanoscale features that are embedded in a macroscopic form. You will see in detail how it is constructed from nanomaterials. So, that is a three-dimensional nanomaterial, nanoporous materials and zeolites. That is how they might look like. That is just an animated image. So, highly porous with a 3D interconnected network. So, these are highly porous with a 3D interconnected network. they'll have if they are highly porous and have a 3D interconnected network, they'll have a very large surface area and a significant pore volume. So now you can imagine the functions that you can utilize from this. There's a very large surface area and a significant pore volume. They are capable of absorbing molecules, ions and gases. So they are capable of absorbing molecules, ions and gases. These are the structural types. They can be a nanoporous network, zeolites or metal organic frameworks. So examples are mesoporous silica, porous silica materials with uniform mesopores that are used in catalysis, drug delivery and adsorption. So you see there's a huge surface area and significant pore volume, so it can be used in catalysis very efficiently. And then there can be zeolite, where a microporous crystalline aluminosilicates used in catalysis, ion exchange and gas separation. Then metal organic frameworks, where hybrid materials made of metal ions and organic ligands are used in gas storage, separation and catalysis. So that's a wet chemical one-step self-assembly of 3D nanomaterials. These include direct growth, surfactant assisted growth or template assisted growth. So you are making 3D nanomaterial from a nanostructure. So how do you proceed? It can be a direct growth, surfactant assisted growth or template assisted growth, and the corresponding SEM images of the fabricated 3D tellurium dioxide nanomaterials. This is obtained from a research paper that the corresponding SEM images, the scanning electron microscopy, you have imaged this 3D nanomaterial from scanning electron microscopy. This is a fabricated 3-dimensional TiO2 tellurium dioxide nanomaterial. So this looks like this in a scanning electron microscope. Under a scanning electron microscope, this is how a fabricated 3-dimensional nanomaterial looks like, TiO2 nanomaterial looks like. Then this is template assisted growth and this is surfactant assisted growth. This is surfactant assisted growth and this is template assisted growth. So that is how it looks like. That is the direct growth. You have nanocubes, then nano rods and then cross-linked nanorods. So you've started from a nano material and you've created a microscopic thing that is cross-linked nanorods. That is how they look like. So that is a single molecular template, and then on the template there is 3D dendritic nanoribbon spheres and then 3D dendritic nanowire spheres. So that grows on this and it forms like and it looks like this. That is a surfactant assisted growth. That is the template assisted growth, lyotropic liquid crystal template, and these are the microspheres, the mesoporous microspheres, and that is the mesosporous nanospindles. So that is how they accumulated and they form 3D nanomaterials, and this is how they look like under scanning electron microscope. 3-dimensional zinc oxide nanostructures. These can be utilized as emitters, as sensors, battery electrodes and photocatalysts. These are the microscopic images of these 3D zinc oxide nanostructures. That is how they look like. The concept of photocatalysts and all I'll be teaching in detail in my next lecture. Natural nanomaterials. So natural nanomaterials are nanomaterials that naturally occur without human intervention. So there are many nanomaterials that are in the nanoscale, they exist naturally. Okay, example viruses, proteins, DNA and magnetotactic bacteria that I will be teaching in detail. So your viruses and protein and DNA, they are all natural nanomaterials. These are naturally of the nanoscale size. Then biological systems have evolved to operate at nanoscale. So you have biological systems and they are already operating at nanoscale. So there are many nanostructures in nature and they are working at the nanoscale. So inspiration, this has formed an inspiration for nanobiotechnology design. So nanobiotechnology design, you will see how your engineered nanomaterials have been inspired from the natural nanomaterials. Sources of naturally occurring nanoparticles. So in the hydrosphere, in the lithosphere, in the atmosphere and the biosphere. So there are sources of naturally occurring nanoparticles all around. In the ocean, seas, in the sea spray, there are nanoparticles. In rivers, lakes and ponds, in groundwater, hydrothermal vents, there are nanoparticles all around. Then in lithosphere, in the soil, rock, soils and magma, and you obtain these via soil erosion, wind erosion, earthquakes or volcanic activities or deforestation, all these create naturally occurring nanoparticles from the soil lithosphere. Then biosphere, microorganisms, plants and animals, as I have already told you, already have nanostructures. Microorganisms, they already have nanostructures inside them, like magnetotactic bacteria, I will be teaching you in detail. Then in atmosphere, in troposphere, stratosphere and lower mesosphere also there are sources of nano particles. So they have been found in moon dust, in cosmic dust and everywhere, in meteorites also. So there are a lot of sources for naturally occurring nanoparticles. So these are natural nanoparticles. So synthesis of natural nanoparticles can also be top down and bottom up. Okay, so it's not like you are synthesizing it only. Nature is also synthesizing it via these two approaches, top down or bottom up. So via wind erosion and weathering in all, rocks and volcanic activity, meaning the weathering of rocks, wind erosion will cause a top down method of nanoparticle synthesis. And volcanic activity and cosmic dust will create natural nanoparticles from a top down approach. Meaning they are being broken down from a huge size to a smaller size. And also there can be chemical precipitation which is bottom up, which can be abiotic or bio-assisted. Via thermal solar energy they will be assembled. As you can see, nanoparticles can also be formed by assembly in natural processes also. Through biomass combustion also, there is a chemical precipitation of bottom up. These are the bottom up techniques basically, where smaller atoms and molecules, they come together to form natural nanoparticles. So these can be found as the constituents of soil sediments, aerosols or colloids. So these are in nature, these are present as aerosols, colloids or constituents of soil sediments. The bottom up approach includes chemical precipitation, where abiotic or bio-assisted techniques are used for smaller atoms and molecules to aggregate into nanoparticles. The small atom molecules create nanoparticles. That is the bottom up approach of nanoparticle synthesis, that is also found in nature, and this happens with the thermal and solar energy. Or biomass combustion can also result in a bottom up approach of natural nanoparticle synthesis. So these nanomaterials are basically found in nature in the form of aerosols and colloids or constituents of soil sediments. That's a schematic representation of the biological features of a magnetotactic bacteria, which determines the prospects for the use as theranostics agents in oncology. So what is a magnetotactic bacteria? It is a bacteria that has some magnetic mineral nanocrystals that align in a certain way, that is known as magnetotaxis. It aligns with the Earth's magnetic field to navigate to places for oxygen. Whatever oxygen it needs, it can navigate to those oxygen specific places by aligning with the Earth's magnetic field. So the magnetotactic bacteria via magnetotaxis can align with the Earth's magnetic field and reach to the places where if it is an oxygen rich place or oxygen rich, whatever it needs, it can reach that place with the help of Earth's magnetic field. So that's a magnetotactic bacteria. It has a flagella for self-propulsion, but for navigation it uses magnetotaxis. That is, it has a magnetic mineral nanoparticles that align in a specific way to be aligned with the Earth's magnetic field and reach to certain oxygen specific places. So these are the magnetic nanocrystals, and and how do you utilize this bacteria for various these are the perspectives basically. How do you use them for biological for nanobiotechnological use? So you do the drug loading like this, and you can move them by magnetic field. So your most of your like magnetic hypothermia, photothermia plus drug release, all these methods have been used already used using this magnetotactic bacteria. It makes it a very very interesting, very adaptable thing to it's a very very useful candidate for bio-nanotechnology. It can be used as an imaging agent for MRI, can be used for guiding and tracking, and it can be used for drug designing, drug delivery, and for genetic or magnetic modifications. So that's the magnetotactic bacteria for you. So engineered nanomaterials. So I've already told you that nanomaterials are being engineered worldwide, and they are all inspired from natural nanomaterials. These are intentionally designed and synthesized by humans, and you can control the size, shape and surface chemistry, and examples can be gold nanoparticles, carbon nanotubes, and these are all tailored for specific technological applications. That's a schematic illustration of different architectures of engineered nanomaterials. So that's a nanosphere solid gold, that's a nanosphere polymeric hydrogel, that's a nanosphere mesoporous silica, that's a nanorod carbon nanotube, that's a nanocapsule which is spion. This is made like this. So all these are engineered nanomaterials. That's a phospholipid self-assembled nanoparticle missile, and that's a self-assembled nanoparticle liposome. This is the hydrophilic part, that's the phospholipid, and they can be nanoshell or natural ferritin, where there is this iron oxide core and apoferritin shell around it, or they can be nanoshell engineered albumin plus drug. The drug is put over here, and that's the albumin shell surrounding it. So all these are engineered nanomaterials. These are used for various functions, and these are tailor-made. You will be using tailor-made properties and using it for your desired purpose. Then the synthetic virus-like nanoparticles. So that's the antigen antibody reactions. So you will be using with this and creating your desired nanomaterial. So these are the engineered nanomaterials that have been made. That's gold and silver nanoparticle, that's mesoporous silica nanoparticles, and these are rutile titanium dioxide nanoparticles. Okay, so these are various structures, and they your optical properties of your quantum dots depend on their structure. So these are 3 atoms, and they all form in the most stable way. Like you have there are the same quantum dot with differing with the number of atoms, and can form different structures, and will have different optical properties. Like you can see a smaller nanoparticle is emitting blue light, a smaller nanoparticle is emitting blue light, smaller quantum dot, and this bigger quantum dot with more atoms and molecules, it is emitting red light. Like I've already told you in my quantum confinement lecture that this is the smaller particle. This will need smaller particle will have a higher band gap between its conduction band and valence band. So it will need a higher energy light to jump from the conduction band to the valence band. So it will emit blue light. Okay, so blue light, which is a higher energy and longer wavelength, or which is a higher energy and shorter wavelength, and or red light, this bigger particle, comparatively bigger particle from the blue one. So this is a bigger quantum dot. It has a comparatively lesser band gap than this one. So it will need a lesser energy and less energy to jump to get excited and jump from its conduction band to valence band. So basically it will need the less energy, that is a higher wavelength light that will emit red light. So this is how it differs, and also these structures are formed according to their stability. Like there are 3 atoms. These are various type of nanozymes. Nanozymes are again engineered nanomaterials. So these are like natural enzymes. You create nanozymes. Certain nanomaterials, they act like enzymes. Like carbon dots, they mimic the hydrogen peroxidase activity of horseradish peroxidase enzyme. So nanoparticles mimic some peroxidase activities, and these so nanoenzymes mimic the peroxidase activity of natural enzymes. So these can be nanozymes can be noble metals, platinum nanoparticles, some transition metal oxides, metal organic frameworks, hybrid structures, carbon nanotubes or carbon based materials, or graphene nanoparticles, gold nanoparticles, these all can be used as nanozymes. These are various type of nanozymes. These mimic natural enzymes and they can be used in various reactions. As you know that enzymes require specific pH and temperature and high level of maintenance and cost. So, these can be replaced by nanozymes that are synthesized. So, these are engineered nanomaterials, and from magnetotactic bacteria also you can create some engineered nanomaterials. These are magnetosomes naturally coated iron oxide with biological membrane constitutively produced by MTB. So, you create that. That is also an example of how your natural materials are inspiring by your engineered nanomaterials. So, natural versus engineered nanomaterials. Your natural nanomaterials are self-assembled, biologically optimized. Engineered nanomaterials are basically precisely controlled and customizable. So, natural your nanomaterials formed by natural processes are obviously they are self-assembled and they are optimized by biologically, they are inherently optimized. But in engineered nanomaterials, you can precisely control and customize the properties and the structure you can control in engineered nanomaterials. Natural system inspires synthetic design strategies. So, your engineered nanomaterials are inspired by natural systems. Then hybrid bioengineered nanomaterials are emerging. So, your natural nanomaterials plus your engineered nanomaterials, your hybrid bioengineered nanomaterials are also emerging. So, this is highly relevant to nanobiotechnology. Dimensionality affects interaction with biomolecules. You know, when you are interacting with a biomolecule, dimensionality will obviously affect, because these are of the small size. So, it will affect whatever dimension you are using. So, surface properties determine biorecognition. The surface properties of your nanomaterials, they determine the biorecognition, as I have already told you about the antibody thing. So, that are used in sensors. So, surface properties determine biorecognition. Natural nanostructures can serve as templates. Like DNA or virus, they can serve as a template and be nano-engineered into your desired material. Then engineered nanomaterials enable advanced diagnostics and therapy. Your engineered nanomaterials have enabled advanced diagnostics and therapy today. They are being widely used in biomedical field. That is bacterial nanotechnology for you, where bacteria is used as a vehicle for various things. That is CRISPR-Cas9, these are bacterial derivatives, or bacteria is also used these are reactive nitrogen production, or in photodynamic therapy, or in magnetosomes therapy, or in gene delivery. Bacterial nanotechnology is widely in use. That is also an example of bioengineered nanomaterials. And bio-inspired nanomaterials, that is a very good example of, so in nature have you seen a chameleon? The chameleon looks like this and it changes color. So, it looks like camouflage, but it does not have any pigments as such that appear green or appear red yellow. These are not pigments, these are guanine nanocrystals. So, a chameleon, basically this reptile you have seen, these have guanine nanocrystals in their iridophores. These animals have iridophores in their skin cells and they do not have pigments, they have guanine nanocrystals. These are guanine nanocrystals and the spacing between them, they can change the spacing between these guanine nanocrystals. So, when light strikes them and the spacing can change, the spacing between these nanocrystals can change when it is either relaxed or excited. So, in relaxed state it looks green and in excited state it looks yellow, but it does not have any pigment change, it just changes the alignment of its nanocrystals. So, it changes the spacing between its guanine nanocrystals and the reflected light changes accordingly. So, the reflected light is being changed now. So, when it is relaxed, the spacing is this much, and when it is excited the spacing goes on to increase. So, the spacing creates a different reflected light. So, it appears green here and it appears yellow. So, it appears green, it is like green blue color when it is relaxed and it appears yellow red when it is excited. So, that is how you see different colors on a chameleon, which has nothing to do with pigment system, it has everything to do with nanocrystals. So, this has inspired a lot of nanomaterials, like it has inspired a lot of nanomaterials, like the color change of an artificial film upon stretching and compression. So, that is an artificial film and you stretch it and compress it and you will obtain different colors. So, that is a bioengineered nanomaterial which is inspired from natural nanomaterial. So, a chameleon in the relaxed state, which is green color on the left and yellow color in the excited state. Okay. These are the transmission electron microscopy images of the guanine nanocrystals that these have, and the spacing between them, as you can see. Summary. So, summarizing, classification basically clarifies the structure function relationship. You know, the structure, the function of a nanomaterial directly depends on its structure. So, it is important to know the structure of a nanomaterial. If you want to create something of a specific function, you need to know the structure of that thing, because these are entirely correlated. Then biomolecules as nanoscale building blocks. So, DNA and all, these are biomolecules as nanoscale building blocks which are being used. Integration of natural and engineered systems. So, as you have already seen, there is a huge integration of natural and engineered nanosystems like DNA. It is a natural material, you can integrate it and create engineered nanomaterial. And then foundation for rational nanomaterial design. So, this has laid a foundation for a rational nanomaterial design. That is a summary. By now, we know that nanomaterials are materials with at least one dimension in the scale of 1 to 100 nanometer range, and at this nanoscale they exhibit unique physical, chemical, optical, electrical and mechanical properties due to quantum confinement effects and the exceptionally high surface to volume ratio, and they are broadly classified in several systematic ways that help us understand and utilize them effectively. So, what does this understanding the classification process helps us in? This understanding the classification is going to help us predict their properties, select appropriate materials for applications, and design advanced systems in medicine, electronics, energy and environmental engineering. So, all this will come when we understand the classification process properly. So, you see how important this whole classification thing is. So, understanding this classification is going to help us predict the properties of these nanomaterials. Second, to select appropriate materials for various applications. Then third, design some advanced systems that are going to help us in like advanced systems for medicine and environmental engineering. So, the most fundamental classification is based on, so we have already seen that the most fundamental classification is based on dimensionality, that is zero dimensional nanomaterials such as nanoparticles, quantum dots and nanoclusters. They have all three dimensions confined within the nanoscale and they show strong size dependent properties. Then one-dimensional nanomaterials including nanowires, nanorods and carbon nanotubes, they possess two nanoscale dimensions with one extended dimension, enabling directional charge transport and high aspect ratios. Then there were two-dimensional nanomaterials like graphene sheets and thin films that have one nanoscale thickness with extended lateral dimensions, and then offering large surface area and excellent mechanical and electronic characteristics. And then there were three-dimensional nanomaterials that consist of nanoscale building blocks assembled into bulk structures such as nanocomposites, nanoporous materials and dendritic architectures. So, all this we have seen by now, we have understood all this. So, nanomaterials are, we also know by now that nanomaterials can also be classified based on composition into carbon-based nanomaterials or metal-based nanoparticles. So, and carbon-based graphenes, fullerenes and carbon nanotubes, or metal-based like gold, silver, iron and metal oxides. So, these polymeric nanoparticles like nanogels, dendrimers, polymeric nanoparticles and composite nanomaterials that combine multiple components to achieve multifunctionality. So, composite nanomaterials that also combine multiple components to achieve multifunctionality. So, another important classification is based on origin, that is natural nanomaterials. This we have also seen in this lecture that another classification was also based on origin, that was the natural nanomaterials like clays and biological nanostructures, incidental nanomaterials produced from combustion or industrial processes, and engineered nanomaterials that were intentionally designed for specific applications. So, That is what we have seen so far. And additionally, structural classification also includes like crystalline, amorphous, and coarser nanostructures. These each influencing stability, reactivity, and performance. And then, in conclusion, the classification of nanomaterials is not merely a theoretical framework, but a practical roadmap. It's a practical roadmap that connects the structure to properties and properties to applications. So it's not just a theoretical, it's not just something to just memorize and learn, but it's a very practical roadmap that connects a structure to properties and properties to applications. So it guides material selection in drug discovery, diagnostics, nanoelectronics, catalysis, energy storage, environmental remediation, and advanced intelligence systems. So, by understanding how dimensionality controls quantum behavior, how composition determines functionality, and how origin impacts safety considerations, and how structure influences performance, researchers can rationally design next generation nanomaterials with improved efficiency, biocompatibility, sustainability, and precision. So, mastering the classification of nanomaterials is foundational for innovation, responsible development, and future expansion of nanotechnology across scientific and industrial domains. So that was the importance of classification. That classification has helped us in understanding structure property relationships, designing nanomaterials for targeted applications, and also controlling toxicity and biocompatibility. Because once you know how the material is classified, you know about the property, and so it also helps in controlling the toxicity and all. And then regulation and safety assessment. For that also, it is very important. I'll teach you in my last lecture about how classification and regulatory and safety assessments are linked and connected. So for example, you know how classification is important for example, in drug delivery, zero dimensional polymeric nanoparticles are mostly preferred, and in nanoelectronics, one dimensional, two dimensional materials dominate, or in catalysis, metal and metal oxide nanoparticles are widely used. So according to the use, you see different classifications are for different applications. And then so basically, to conclude, in this lecture, what we have learned so far is that nanomaterials can be systematically classified based on dimensionality, composition, origin, and structure, and each classification provides insights into their behavior, performance, and applications. So as nanotechnology advances towards intelligent systems, theranostics, and micro nanorobotics and sustainable technologies, understanding nanomaterial classification becomes very essential for innovation and responsible development. So, in other words, the importance of classifying nanomaterials lies in creating a clear framework to understand and control their behavior at the nanoscale. So, because nanomaterials exhibit properties that drastically change with shape, size, composition, and structure, classification helps to organize this complexity into meaningful categories. So, it allows researchers to predict how a material will behave even before it is synthesized, saving time, cost, and experimental effort. So, in a nutshell, researchers can predict how a material will behave before synthesizing these materials, cutting down the cost, time, and effort. So, by grouping nanomaterials according to dimensionality, composition, morphology, and origin, scientists can systematically relate structure to properties and properties to performance. So, classification supports rational material design. Another example is that if high surface area and rapid drug release are required, one may select zero dimensional polymeric nanoparticles. And if directional conductivity is needed, like I've already told you, if directional conductivity is needed, one dimensional nanomaterials are nanowires are preferred. Or if mechanical flexibility and high electron mobility, these are all essential, then two dimensional nanomaterials like graphene become suitable. So I've already told you about this. So classification acts as a decision making tool in research and industry. And beyond design, classification is equally important for safety assessment and regulatory control. Different classes of nanomaterials interact differently with biological systems and the environment. So, categorizing them helps in evaluating toxicity, biocompatibility, environmental impact, and long term stability. It also aids policymakers and regulatory bodies in establishing standardized guidelines. So, classification is very important for the safety assessment and regulatory control. I'll tell this in detail in my last lecture. So, most importantly, classification enhances communication across disciplines. Engineers, chemists and physicists and biomedical researchers, they can all collaborate more effectively when materials are systematically categorized. When materials are systematically categorized, they can be a multidisciplinary, a better communication. So, classification of nanomaterials is not just merely descriptive; it is a foundation for innovations, safe application, interdisciplinary research, and the sustainable development of sustainable advancement of nanotechnology. Thank you. Thank you for listening.
Hello, good morning everybody. I am Raghunandan Sengupta. So, I will just give you a very brief excitement area of finance, which is quantitative finance, and that has a huge market starting around about 10 years back, and it is exploding exponentially. So, what do we mean by quantitative finance? Quantitative finance is actually the application of different mathematical and statistical techniques in the area of financial markets, be it say for example derivative pricing, be it in the area of say for example portfolio management, be it in the area of asset liability management, be it in the area of portfolio management. We see that the application has exploded in such a way that there is a huge opportunity for people who have a quantitative background in mathematics and statistics. They can utilize those in the area of finance, but obviously with some prior knowledge of finance as a subject. Now, when we say about quantitative finance, as I said, it is an area of applied mathematics and statistics applied in financial markets. Use of different areas, if somebody is interested to know, we have stochastic calculus, we have derivative pricing, we have operation research, we have quantitative techniques like differential equations, stochastic calculus, time series, and they are heavily used in the area of quantitative finance as I mentioned. Now, we all know that in 1997 the Nobel Prize in Economics, so it is basically the Nobel Memorial Prize in Economics was given to the work of Merton and Scholz in the area of derivative pricing, and after that there has been exponential increase in the area of quantitative techniques in quantitative finance and in the area of different type of derivative pricing. With the advent, moreover with the advent of high ended and sophisticated computing data, big data has come in a very big way, where application areas starting from computing, from different type of algorithm design have been taken up in such a big way that nowadays at least we are able to understand that how high frequency data algorithm trading can be utilized using the concept of quantitative finance in the area of finance as such. But there is a flip side also, obviously when there is a huge amount of development. So, obviously due to some regulation errors or something, there has been some pitfalls, which I think is should be a bullet point for people who are really interested to take up quantitative finance, they should be aware. So, consider the financial crisis in 2008 and later on, and we are seeing different banks are failing, different financial institutions are facing a problem, countries are facing a problem like in Europe, in USA. So, what should be done? So, the main thing is that even if you know the technique is best for people who are investors, who are private players, organizations like banks, governments should use these techniques in a very somber manner, such that the application areas of quantitative finance using the techniques which we learned can be utilized in the best possible way to garner the overall the in-depth knowledge a person has in trying to utilize these quantitative techniques in finance. And I am sure that people who have the background, who have the knowledge, who have the sophistication, who have the knowledge of the society can definitely use quantitative finance in a very big way in trying to make their mark in this exciting field, which you are going to see in years to come. And I am sure it will be a very exciting learning tool for all the participants who will take quantitative finance as a subject in years to come. Thank you, and I wish all the participants all the best and best of luck for the programs they will take. Thank you.